Here we need to determine an appropriate chemical formula given the spectrum below. Now, if we look down a little bit further in this problem, we find the following table. And the most important piece of information we get from this table is the fact that we have these two peaks that are exactly 2 mass units apart. And given that the M+2 peak is slightly lower in intensity than the initial parent peak, that tells us this molecule almost definitely contains a bromine. Now, the other thing we can get from this is, given that this mass here is odd, in general we know that an odd mass tells us that we have an odd number of nitrogens. So at this point, I'd be comfortable in assuming that this molecule is going to, of course, have some number of carbons and hydrogens, as well as a single bromine and a single nitrogen. Now, it's always useful to keep track of where we are with the mass. So 185. Now if we subtract out 79 for the bromine, and another 14 for the nitrogen, we're left with a total currently of 92. At this point, we know the molecule will have to have less than 8 carbons, because 8 carbons would give us a mass of 96. So 7 carbons gives us a mass of 84, whereas 6 carbons gives us a mass of 72. The problem with 6 carbons and a mass of 72 is that would mean we would have 6 carbons plus 20 hydrogens in this molecule. And that's not mathematically possible. But if we have 7 carbons, we subtract out 84 from our mass, we have a total of 8 left, and we come up with a chemical formula of C7H8Brn. And this works because it satisfies our mass for the parent peak, as well as the isotope pattern, which showed the bromines, as well as having an odd number of nitrogens based on the odd mass in this molecule.